So back in 1924, Louis de Broglie proposed that particles could have wave-like character in addition to their particle character. So for electrons, we see the wave nature of an electron in electron diffraction. So we looked at how waves of water and waves of light can diffract. Remember the guy with the box on the beach, right? And the little dots of light that were kind of spreading out. So electrons will also diffract and form a pattern like that. But what's really kind of freaky is the interference is not caused by pairs of electrons interfering with each other, but by single electrons interfering with themselves. So here, the electron is not behaving like a particle. A particle can't go through two slits at the same time and interfere with itself and produce a diffraction pattern. But a wave can. So here the electrons are behaving like waves. So this is what we would see if you get an electron source and you're shooting electrons at this plate and there's two narrow slits. The actual electron behavior is this. This comes through and it makes this interference pattern just like the sunlight did in the box with the double slit experiment. It's electromagnetic waves. Well, I guess it's waves. It's electron waves. But it's waves and they interfere with each other. We could not observe this pattern if the electron was not behaving like a wave. If the electrons were behaving as particles and we're shooting electrons at this wall here, we would expect to see a straight bright spot over here and a bright spot over here corresponding to those two slits. And that's what one of the guys on the beach thought he would see, right? You have these two little slits, it kind of makes sense. You can see two white stripes on the bottom of the box. But that's not what they saw because light is a wave and it interacts with itself and it creates this diffraction pattern. So this is what we would expect if waves and electrons were behaving as particles. So questions? No? I think a lot of times when I ask if people have any questions, people are probably thinking, well, heck yeah, I got a lot of questions, but I just can't even put them into words, right? Like, okay. So the wave nature of the electron is a property of individual electrons. So de Broglie predicted that the wavelength of a particle was inversely proportional to its velocity. So this is the de Broglie relation. Here we have the wavelength of light is equal to Planck's constant that has this value, divided by the mass times the velocity. And, I just really wish they had chosen some different letters here. Because velocity is a v, but when we type a v in a mathematical equation, it's usually italicized. Frequency is the Greek letter nu, which looks disturbingly like a v, right? So, yeesh. You look at this out of context, and it's really hard to say what that is. The de Broglie relationship relates wavelength to velocity, not to frequency. Whoops. So let's do an example problem. What's the velocity of an electron that has a de Broglie wavelength approximately the length of a chemical bond? Assume this length to be 1.2 times 10 to the minus 10 meters. So we're given this number, and we're asked, what's the velocity? So that number, 1.2 times 10 to the minus 10 meters, what quantity is that? The wavelength? So it says it has a de Broglie wavelength approximately this length, assume that to be this. They could have said, just come out and said, it's got this wavelength. But I don't know why they do that. So we've got the wavelength, and we're trying to find the velocity. This is when we're going to need this equation here. So the wavelength is equal to h over m times nu. And h is that funny number, 6.626 times 10 to the minus 34. So h is 6.626 times 10 to the minus 34 joules times seconds. And we've got wavelength is equal to Planck's constant over the mass times the velocity. And that velocity is what we're trying to find. We've got the wavelength, we've got h, we're trying to find v. What are we missing? The mass of an electron, right? Hey Siri, what's the mass of an electron in kilograms?
Here's what I found from byjuice.com. The mass of an electron is 9.1093836 times 10 to 31 kilograms.
She meant 10 to the minus 31 kilograms. That's not a number I remember. So we looked that one up. Okay, to solve this for v, we need to rearrange the equation. You can use the number solver on your calculator. If you don't have that, what we want to do is we want to cross multiply to get rid of the fractions. So those things and these things. So we end up with lambda times mass times velocity is equal to h. And then we can divide, and we end up the velocity is equal to h divided by lambda times m. So h is 6.626 times 10 to the minus 34 joule seconds, divided by the mass, 9.109 times 10 to the minus 31 kilograms. Oh, I put them in the wrong order. Please forgive me. And the wavelength. I switched these, but order doesn't matter when you're multiplying, so it's okay. If we look at those the units there, they don't seem to work out very well. But if I remember correctly, a joule is a kilogram meters squared per second squared. So if we multiply that by S, then one of those cancels out. And if we divide by M, one of those cancels out. And we divide by kilograms, that one cancels out, and we end up with units of meters per second. You don't need to be able to do that. You just have to believe me that it's okay. You want to use kilograms here so that the units work out. Do you think this electron is going really fast or really slow? I heard a mumble, but I didn't understand it. It's okay, you don't have to commit. We'll find out. being 6.1 times 10 to the 6th meters per second. Not as fast as the speed of light, but still really, really fast. Make sure that you can get your calculator to give you that answer, because this is another one of those places where we are dividing by two things multiplied. And so the way we think about it in our heads is not always the way that the computer thinks about it. Well, that was a little too fat. So you'll want to use parentheses if you want to multiply those things in the denominator. Otherwise you'll get some other crazy answer. Any questions? So here's a conceptual problem. Since quantum mechanical theory is universal, it applies to all objects regardless of size. Therefore, according to the de Broglie relation, a thrown baseball should also exhibit wave properties. Why don't we observe such properties at the ballpark? A, because of the baseball's large mass, its de Broglie wavelength is minuscule and insignificant compared to the baseball's size. B, since baseballs do not have any charge, quantum mechanics does not apply to them. Or C, quantum mechanics does not apply to baseballs. So this is one of those multiple choice questions where if you're a good test taker, you don't actually need to know anything about quantum mechanics. Because what does it say up here? It applies to all objects, regardless of size. Quantum mechanics applies to everything. So, is B true? That because baseballs don't have a charge, it doesn't apply? No, it just said that it applies to everything. How about quantum mechanics doesn't apply to baseball? Quantum mechanics applies to all objects. So it's got to be A. The larger the object, the smaller its wavelength, right? So if you have a big visible object, it does have a wavelength, but its wavelength is so tiny that you can't see it, right? The smaller the thing gets, the larger its wavelength gets. Any questions? There's a couple questions on the worksheet where it asks you to calculate de Broglie wavelengths. The uncertainty principle. So if you try to observe the wave nature of the electron, you can't observe its particle nature. And if you observe the particle nature, you can't observe the wave nature. And this gets back to Schrodinger's cat, where the cat is either dead or alive inside the box. But until you look at it, it's essentially both. But it can't be both at the same time. Well, the quantumly small things can be both at the same time, but we can never see them be both. So if you look at one state, you'll only see that. If you look for the other state, you'll only see that. So our evidence for electrons is the wave nature is demonstrated by their interference pattern. The particle nature would be demonstrated by the position, which slit is the electron going through. Because if it's behaving as a particle, it has to go through one slit or the other. A particle cannot go through both slits at the same time. So these are said to be complementary properties. The more you know about one, the less you know about the other. So if we design an experiment to detect where the electron is, which slit it's going through, and we could do this by using a laser beam here, and we would be able to detect the electron going through the laser beam. You shine that laser beam here, and the interference pattern goes away, and you get two lines. The electrons behave like particles. You turn off the laser beam, you see the interference pattern. What I want to know is, how do they know that we're observing them, right? Well, they don't, but it's just a very, very strange thing to think about, right? So you can either see them behaving like waves, or you can see them behaving as particles, but you can't see them doing both. Sorry, it's disturbing. So Heisenberg came up with this uncertainty principle, and I think there's a couple of homework questions maybe, and there's a question or two on the worksheet. Other than that, this is really not a big deal in terms of the equation. It's more the concept. So this is his equation, and you definitely don't need to memorize this. So delta x refers to the uncertainty in the position of the object. And delta v, this is v, not new, delta v is the uncertainty in the velocity. So the uncertainty in the position times the mass times the uncertainty in the velocity is greater than or equal to this value, which is Heisenberg's, the Planck's constant, that's what it is, sorry, there's two h's here. Planck's constant divided by 4 times pi. So what this says is, the smaller the uncertainty in the position, the greater the uncertainty in the velocity. The more you know about one, the less you know about the other. We can't simultaneously measure the position of electron and its velocity. We could measure its velocity, but then we really have no idea where it is. If we identify its position, we can't say much about its velocity. You just can't know both things at the same time. So which statement best summarizes the uncertainty principle? Both the position and the velocity of an electron can be accurately known at the same instant. Either the position of the velocity can be known at the same instant, or neither the position nor the velocity can be accurately known. A, B, or C? I think the train said B. The answer is B. You can know one or the other at a given instant, but you can't know both. So this one's not true. You can't know both. This is also not true. It's not true that you can't know either of those things. You can know one or the other. Any questions? So we mentioned determinacy earlier in this chapter. That's classical physics. Particles move in a path determined by the particle's velocity, position, and forces acting upon it. The present situation of an object determines what it's going to do in the future. You throw a baseball, and you can predict what's going to happen. Our brains are doing all kinds of incredible calculations when we learn how to catch a ball that's thrown at us, right? Babies, small children have trouble with that. But then you go out and watch the professional baseball players, right? Or football receivers. Oh my goodness, right? They're running and the ball's coming and they end up in the same place and they catch the ball. Do you know how amazing that is? How would you calculate all those factors? It's insane. It really is. But we can predict what's going to happen. With electrons, we can't know the position and the velocity, so we can't know what it's going to do in the future. That's called indeterminacy. The future can only be described statistically. You can say, well, this is more likely to happen, or there's a certain chance that it's going to be over here, but we can't do what we do with like a ball that's thrown. We can describe the probability that an electron will be found in a particular region. And that uses really complicated statistical functions, a probability distribution map. So here's an example with baseball. Batter hits the ball is flying through the air, there's a whole bunch of forces acting upon it. Big one is gravity pulling it down. The outfielder here sees the ball, his eyes determine how fast it's moving, and he knows the effect that gravity is going to have on it, and so he can position himself and catch the ball. That all makes sense to us. This is more like what electrons do. So here we're looking at a pitcher. So the pitcher's pitching the ball and it comes over the plate. Right? If he pitches the ball in exactly the same way every time, it'll go in the same place. Or if you think of a pitching machine, if you don't think that a pitcher has that much control, a pitching machine set to, shoot the ball out exactly the same way every time, it's going to go in the same place, right? If you were to do that with an electron, it would not go in the same place every time. It'd go all over the place. Not literally all over the place. So throwing an electron at this catcher, there's a 20% chance that it'll be in this smallest circle, a 40% it'll be within this range, a 70% chance that it'll be within this wider range. All of those dots would represent electrons with exactly the same force and position and all the forces acting upon them, but they do different things. Does that bother you? It bothers me. So, yeah, most of the time it comes over here, but one of these electrons could come and hit this lady right between the eyes. That's not impossible. Improbable, perhaps, but not impossible. Any questions? You must have some questions. Or maybe it's just a bit weird.